For this lesson, we're going to continue to take a look at essentially at exponent laws. We started off our lesson in this unit by looking at exponent laws that I hope was at least something of a review for you. Here are those exponent laws when you have the same base. So for example, the base here is a. So a to the power x times a to the power y, we add exponents. For division, we subtract exponents. There is a rule here for how do you handle positive to negative exponents and power to a power, so an exponent raised to another exponent, and then just general rules. A to the 0, anything to the 0 is equal to 1, so long as it's not equal to 0. So 0 to the 0 is undefined. We don't know what that means. We also have a couple of exponent laws if the bases are different. So you should refresh your memory on these things, go back and look at the previous lesson if necessary. Today we're going to be taking a look at what are known as rational exponents. So we're still looking at these exponential expressions, but a rational number, if you need to recall that, a rational number is something that can be written in the form m over n, where both m and n are integer values. So that's a rational. And we normally think of a rational as a fraction. For example, 2/3, that's a rational number. The number 5 is also a rational number because we could write 5 as 5 over 1, an integer over another integer or divided by another integer. So that's something to keep in mind talking about rationals. Now we've got this kind of hypothetical situation. We've got a cube of side length x, so x by x by x. That means the volume of that cube would be x cubed, and the area of a single side of that cube would be x by x, or x squared. This is a purely hypothetical question, so how could I write the side length x in terms of the volume or the area? I want to write it as essentially a power relation. Here I have a power relation. I'm saying v equals x to the power of 3. So how about reversing that? Now if you take a look at this one, especially if you think of it this way, a equals x squared, I'm sure that many of you have a very good idea of how to write this the other way, which is x equals something involving a. But the path I'm going to take, because I'm specifically interested in the idea of rational exponents, the path I'm going to take is actually a little counterintuitive, which is why we get taught this as opposed to having to come up with it on our own. So the first thing I'm going to start with here, I've got x equals v to the n, and essentially I want to know what is the value of n that makes this relationship true. So where I'm going to start, I'm actually going to start with the relationship that we established from the diagram, which is that volume is equal to x cubed. And now into this, and this is a very odd step, I'm going to sub in, sorry, it's not to the m, it's to the n. I'm going to sub in this new relationship. So that means that I have v equals, but instead of x, I'm going to replace my x with v to the n. So this x becomes v to the n, and that thing in the brackets, which used to be x, is cubed. But now I can make use of one of our laws of exponents, which is v to the n all raised to the power 3 is actually, I can multiply these together and I end up with v to the 3n. Another one of our, it's not so much a law of exponents, but it's one of the conventions for exponents, which is here I just have v, but when I just have a variable or even a number and there's no exponent written, that exponent is understood to be 1. So this is saying v to the power 1 is equal to v to the power 3n. In mathematics, that type of relationship implies something else about these values. So if v to the power something equals v to the power another thing, then mathematically that means that those two exponents must be equal to each other. And from here, I end up with n is equal to 1/3. I can do the exact same thing here. I'm going to start with area is equal to x squared. I'm going to sub this strange expression, a to the power m, x is equal to a to the power m, and I end up with a equals, now wherever I had an x, I'm going to replace it with a to the power m. So instead of an x, I put a to the power m, and that's all squared. Using our exponent laws from before, same as before, we get a to the 2m here, and we recognize that this is a to the 1 equals a to the 2m, which implies that 1 is equal to 2m, m is equal to 1/2. So I can take those two results. So this one means that x is actually the same thing as v to the 1/3. X is actually the same thing as a to the 1/2. Now, I'm sure many of you recognized it here, but I expect all of you recognize this one. We could have written that x was actually equal to the square root of a. And so a to the 1/2 is actually equivalent to the square root. We could have written x is equal to the what's known as the cube root of v. So v to the 1/3 is equivalent to the cube root of v. So this is a very important relationship, the idea that a rational exponent has some relationship to radicals. In this case, it's kind of like what we had up here. A with no exponent visible means the exponent is 1. A radical, or a root, with no index visible means that it is understood to be 2. If you want something like the cube root, you must write the 3. Okay, so here is that rule. If we have this very specific form of my exponent, 1 over an integer, so b to the power, so b is the base, to the power 1 over n, then we can say that is equivalent to the nth root of b. When you're doing these roots, n has to be a value greater than 0. You can't take the -2 root. It has to be the positive. So it has to be a positive integer. Other restrictions that we've run into before in the course, you're not allowed to divide by 0. Our course wouldn't be the first time you've seen that, but we've made quite a bit of use of that. And you're not allowed to take the even root of a negative. So you're not allowed to take things like the square root of -2. You're not allowed to take things like the 4th root of -2. You're not allowed to take the 6th root of -2. Now, moving on to an exercise. I've got more room on the next page. I just put this here as a bit of a preview. So I want to express each of these in radical notation and then evaluate them. So radical notation, write them as roots. Evaluate what is the numeric answer. So first, radical notation. This is the number 10,000, but it is the 4th root of 10,000. That is the same as asking what number multiplies by itself 4 times to give me 10,000? And the answer to that is 10. This one has a base of -8, so you need to keep that whole base together, and that's a cube root of -8. Students have a natural aversion to when they see the negative sign inside a root. They think, well, that's just not allowed. I'm not allowed to take the root of a negative. One of the things we really want to clarify in this lesson is, well, first of all, you are allowed to take the roots of certain types of roots. For example, you can take the cube root of a negative. Even if this was a square root, we could still write this, but then we'd immediately say that that answer is inadmissible. But in this case, the cube root, what number multiplies by itself 3 times to give me -8? And the answer to that is -2. Now this one, 49 to the -1/2, once you become more comfortable and familiar with exponents and exponent laws, there's a couple of ways to do this, but I'm going to start with what I think is the most straightforward. Using one of the exponent laws we looked at in a previous lesson, this is 49 to the power -1/2. When we're dealing with radicals, when we're dealing with roots, we want to have positive exponents. So I'm going to rewrite this as a fraction. So I'm going to write this as 1 over 49 now to the +1/2. That's one of our laws of exponents. Now I can deal with that using our rules for rational exponents. So I can write this as the square root of 49, but we don't normally put the 2 there. It's understood. And the square root of 49 is 7. So my answer here is 1/7. How about this one? I've added this complication. It's not a 1 anymore. I've got a 2 there. So what can I do to deal with this? Once you become comfortable with this, you're going to go immediately to the answer. But to start, what I'm going to do is I'm actually going to make use of this rule, which is that a to the x to the y is the same as a to the xy. So that's saying I can take these two things and multiply them together. How can I write the number 2/3 as the product of two numbers? Well, I could write it as 2 times 1/3, or I could write it as 1/3 times 2. Either order is fine. Now, in this case, I actually have a preferred order. So I'm going to, well, you know what? I'm just going to go ahead and start with it the order I wrote it here. Let's just go ahead and be honest. So I'm going to write this as 27 squared. So there's the first number. And then that's all to the exponent 1/3. Because by our exponent laws, 2 times 1/3 is 2/3. So this is the same thing. These are equivalent. The reason why, and I'll tell you up front, I don't like doing it this way because I take a look at 27 squared, and yeah, that's something that I might do in my head, but it's not something that everybody's going to be comfortable doing. So you get 729 now to the 1/3. You could have gone straight to this notation, the cube root of 729, and I just wrote that backwards. 729. And again, if you happen to know what the cube root of this is, that's all well and good. But these larger numbers, I don't expect people to necessarily know that the cube root of 729 is 9. Even there, if I suspect that the answer is 9, I'm going to use my calculator to verify that. So since I just happen to write this out this way, well, what's my preferred method? I would rather do this way. And you can decide for yourself if you agree with me, because this is still correct, but take a look at my other proposed method of doing this. 27 to the 2/3 is the same as 27 to the 1/3 all to the power 2. You might think, well, big deal. You haven't really done anything new there, but it is quite different. Inside the bracket is the cube root of 27, and that's all squared. Now the cube root of 27 is a much simpler number. The cube root of 27 is actually 3, and that's squared, and we end up once again with 9. So why is this better? The reason this is better is because the cube root results in a smaller, so it makes whatever it's operating on, if it's a number bigger than 1, it's going to make it smaller. Whereas squaring it will make it larger. So I think it's a good idea to make your value smaller first and then make it larger, as opposed to this other method, which makes it larger first and then makes it smaller. I find that if you do it this way, you might have less need for a calculator. And that, I'm going to admit up front, is my own bias. I prefer to do without a calculator whenever possible. even if I have to use a calculator, I prefer to at least have an intuitive idea of what my calculation is going to turn out to be. Okay, how about this next example? Now this one I'm only going to do one way. I'm going to do it my preferred way. So there's my base, which is negative 27. You're going to want to use brackets here to make sure you do things correctly. It's all of negative 27 to the 1/3, and then that whole thing to the power 4. 1/3 times 4 is 4/3. So I'm going to write this another way. You could have gone straight to this if you'd wanted to. That's the cube root of negative 27 to the power 4. This is the cube root of a negative. It's an odd index here, so that's allowed. And so we end up with negative 3 all to the power 4. But negative 3 to the power 4, that's that's an even exponent, which means we're going to end up with a positive result, and we end up with 81. So in summary, if we have a generic rational exponent, which means not that easy version, which was 1 over an integer, but in this case, we have an integer over another integer. We can write that, we take from the denominator, that becomes the nth root, and then overall to that exponent. Or we could do the base to that exponent and then take the nth root of the overall. I've mentioned already that this one is my preference. So my initials, this is the one that I prefer right here. But like I say, they're still both correct. Also, a correction here. M does not have to be positive. N must be positive, but M can be positive or negative. We can deal with negative exponents because we know this rule, that a to the negative x is the same as 1 over a to the positive x. So even if the numerator here is negative, we can make it positive using this exponent law. Just a reminder, I've spoken about this throughout the lesson. We've seen examples of it. We are not allowed to take the square root of a negative number. This is something you've probably known for quite some time, and that's because no real number multiplied by itself will be negative. This is also true for higher order even roots, so 4th root, 6th root, 8th root, etc. Odd roots, on the other hand, you can take a negative root, a cube root, a 5th root, a 7th root. So just something to keep in mind. It's something people are going to trip over. Just watch out for it. I'm just trying to provide you with a warning. And there's our assigned work, not from our textbook, it's from another textbook. I'll also post this on the web page so you can refer to it there.